did we kind of poach? What distribution did we kind of poach when we started studying about this stuff? Do you remember the distribution when we were doing the coin spins, on foreclosure rates, even unemployment rates? Remember what the distribution was that we poached originally? Remember him? The binomial? We poached him. We said, oh, this sounds like binomial, because either the coin lands heads up or it lands tails up. Either a house that we grabbed for sale is in, or it's binomial, right? It's binomial. So all this makes sense, except there's one thing that doesn't kind of make sense. At some point, another distribution showed up. Did you catch what had happened? You might not have caught it. You also might not care, that's okay too. But did you catch where another distribution made itself known on this slide right here? And it's not even discrete, which makes it really weird. It's a continuous distribution. Where is it? Where is it? There's only one letter. I'll give you a hint. I was bitching about this subscripting that didn't get saved last time. Ha! Him. Remember him? Z-scores? Z-scores exist where? On a... Now what the hell? Why am I mixing and matching bell curves with the binomial distribution? Binomial is discrete. Normal distribution is continuous. Why the mix and match? Well, I think I don't have a good answer for that yet. I'm still researching that one, but I think I have a good explanation. If it's not the answer, I'm going to call this the answer. So here's my logic. Let's get to the quiz. We just did that. Okay, I'm going to set up something you guys saw. Don't write this down. This is already available to you online. It's a lot of graphics that are coming at you pretty quickly. So suppose you've got a binomial from 243 that has an average of a half and an increasing sample size. You looked at this back in 243, and you know that as the sample size goes up, what happens to the binomial curve? It starts to bell out, doesn't it? It starts to shrink in, and the tails become less likely, the middle becomes more likely. So, in other words, binomial distributions do look like bell curves if your sample size gets quote-unquote large enough. Right now, your sample's at 100, which is far below the samples we've been pulling from these studies, 702, 1102, and things like that, far below. So you can clearly believe that as the samples grow even more, they'll look more and more like bells. In other words, the stair steps, the stairs connecting them get smaller and smaller and smaller, and they look more like a smooth curve. Is that fair? Okay, hopefully that's fair. Good. But here's the problem. This makes the assumption, a very dangerous one, that the proportion is at 0.5. Remember, the point of this lesson was to estimate what that p is, not to tell me that p is 0.5. It's to estimate the value of p. This is making a dangerous assumption that p is right in the middle between 0 and 100%. That's one aim, isn't it? Probably like, dude, I was going to say the exact same thing. So what happens if it's not? So what I'm going to do now is, I'm going to mess with that value of p. So what happens if we let the value of p start to vary? Right now it's at a half, yes? Right now it's at a half. What happens if it goes to 40% or 30%? Or take a look at those curves and what's starting to happen. Look at the top especially. 0.1. What is this now? What is that? Oh, crap, hang on. Too much automation. I apologize. Where did our bell curve go? Oh, it's skewed, highly skewed. Alan, what'd you say?
Moved to the left.
It moved to the left. We lost the tail, yeah? This is what I'm really concerned about, is that tail's gone. It can't exist. You can't go below 0. If you've got a sample size of 20, I think this is it, sample size of 20, if there's a 10% chance of success, you can't go below 0. This is like buying 20 birds and plot the number of roosters that you get, right? Plot the number of roosters that you get. You're going to expect 2 out of 20, which is 10%. You're not going to expect 20 roosters or 19 or 18 or so forth. But the problem is, you've got this tail but no tail over here. I forced a bell curve onto it. Apologies, it looks like crap because it's missing a tail, which means that we got an issue with the bell curve. So this almost makes it seem like we shouldn't be using a bell curve with the binomial because they don't agree with each other. But that's where sampling fixes. Sampling fixes everything. What we're going to do, this is only a sample size of 20, correct? This is only a sample size of 20. Watch what happens if I use the exact same, very exaggerated percentage of 10%, but now I start increasing the sample size. So if you think about it, a sample percentage, or a population percentage of 10% is about what our foreclosure rates were looking like over here. 9.7%, 8%, things like that, and so forth and so on. So in other words, we've got this issue, this skewed issue, with our sample percentages. Well, we can fix that by sampling more than 20 homes. Look what happens. Okay, there's the original situation. Now let's go, sample size of 40. Sample size of 60. What's happening? What are we getting at? We are starting to get a bell curve. Okay, automated happy. Apologies. Back up one. Did you catch? I'm getting happier and happier the larger I'm drawing. I'm getting happier and happier. That looks like a bell. Damn it. Stay there. That looks like a bell curve. There is an issue, of course. There is an issue with this. If the sample size is 100, this starts at 0 and only goes to 20, yes? Which means there is 21 through 100 over here on the axis. But here's the deal. If you have a sample of size 100 and your proportion is only 10%, you shouldn't be getting things over here, should you? I mean, you shouldn't be seeing that. If you're seeing that, either this is not 10% or you're drawing crazily deviant data somehow. Goes back to Alan's question about the bias. So, the lesson taken away, this is my answer to you guys. This is my answer to you guys as to why we're mixing and matching the binomial and the normal. As long as you have enough data, and this is kind of, we're going to keep visiting this idea over and over again in this course, as long as the product of your sample size and your assumed population proportion is at least 10, and this is the sample size times proportion of failure is at least 10, you can feel okay using a bell curve to provide your margin of error estimate for those z-scores, because the binomial and the normal look the same. Anybody wondering, why don't we just use the binomial completely and do a little extra work? Is anybody wondering that? Okay. You already answered the question on that quiz if you did it this week. If you did this quiz with the Excel, with the F9, you answered the question. This is how you do that. Anybody use the normal distribution on this? Anybody pull out the normal program to do this quiz? Hopefully not. You didn't have to. But when you gave me the graph with Excel, what's I'm looking for here? Hang on. When you gave me this, damn it. Oh, they're all mixed together. When you graph on Excel, and I had to take a screenshot and put it on the paper, what did it look like? Bell. Like a bell shape, didn't it? So why force a bell curve? It's already going to be there automatically. I guess that's my point. And the answer is, in 15 more years, we won't be doing these assumptions anymore. We'll just let the data show us itself. But we're not there yet. So I'm trying to find, in where we are right now, here's an explanation of why you actually are okay using those little z multipliers. Now, I say using the z multipliers, the TI is doing it for us automatically. We're not doing anything, it's doing it automatically for us. So, questions you have right now, if you have any right now. If you want mathematical proof, which I'm guessing 0 of you do, maybe 1. It's all on the enrichment page. I've got proofs of all these statements for you if you want more rigor than just an Excel spreadsheet replicated over and over again.